All right, so now we don't always have such a complicated connection geometry as we do here on this truss bridge. So I kind of simplified it. This is kind of a typical plate-to-plate connection. So about 6 bolts. We're looking at a 8-inch wide by 1-inch thick plate, and it's connected to a 10-inch wide by 1-inch plate. Now, as we can expect, as we pull on this member, we're expecting the 8-inch member to fail first. And we want to come up with the capacity for that. Now, as we pull, we might expect that somewhere over here, this gusset plate will yield. And so when that yields, it will cause stretch, right? Now, that area that's stretching, that area is this surface here. And so looking at that, that's this cross-sectional area that is subject to yielding. So when we go to come up with our design strength, we're going to use what we call the gross area of this cross-section to come up with how much strength this can hold for the limit state of yielding.
So now we're going to solve example 1. Let's start with part A, which is going to be to calculate the strength of this connection, the design strength, assuming that all the plates are made out of A36 steel. Now, like we saw on the bridge there, we have to come up with an expression, and we're going to start with coming up with the yield capacity of these members. But before I do that, I want to think about the two members I have. Right? I have a PL 1 by 8 member and a PL 1 by 10 member. Okay, so they're both 1 inch thick, but which one's going to control? Hopefully you guys have come to the conclusion that the PL 1 by 8 is going to be more critical, right? Because that only has a width of 8. The other one has a width of 10. They're the same thickness. So the PL 1 by 8 member has less area and will therefore be more critical for both yielding and fracture. So the calculations in this example problem are going to focus only on the 1 by 8 member. All right, so let's come up with a value for the yielding. Now for the design strength, right, we're looking for a force that we can apply to the connection. So we'll write our general equation. P sub u has to be less than or equal to phi pn. This is our general design equation. And I'll add a little sub t there on phi. That's just phi for tension members. All right, we know if we look up in chapter D in the AISC manual, we'll find that phi for yielding is 0.90. Now we have to come up with some expression for Pn. I want to refer back to the steel stress strain curve, and right when we go back to elementary mechanics, stress is equal to P over A, so I can rewrite that as P is equal to the stress times A. So that's going to be the basic formula that we're going to use to come up with the yield capacity and also for the fracture capacity. Basically, a stress times an area will give us a force. So for yielding, we're concerned about yielding in the gross cross-section. So we're looking at the yield stress times the gross cross-sectional area. And as I previously mentioned, the phi, our safety factor for our reduction factor for LRFD is going to be 0.90 for yielding. So let's put that all together into our equation. So P sub u is going to be less than phi, which is 0.90, times Fy times Ag. We were given that this was A36 steel that we were dealing with, so that means that Fy is 36 KSI. And again, you can refer back to AISC table 2-5 if you want a quick listing for where these materials are kind of compiled in our manual. And lastly, we need to come up with the gross cross-sectional area. That was the area at the end of the member. So for a 1 by 8 member, that's going to be 1 inch thick by 8 inch width. so a total of 8 inches squared for this particular member. Now all we have to do is multiply everything together. So we get for this particular limit state for A36 steel that P sub U has to be less than or equal to 259.2 kips. Alright, let's move on to fracture. So for fracture, we're going to have the same basic design equation that P sub U has to be less than or equal to phi Pn. So now we need to come up with a capacity, a nominal strength for fracture. Again, we're going to follow the same basic principle that we did for yielding, except at fracture, we're worried about physical separation of the member, and that occurs after we reach the ultimate stress, F sub U, of the material. So here for fracture, we're going to consider F sub U. However, we are concerned with fracture at what we call the net section, and so we're going to use the area at the net section because that's where the member will fracture first. And I'm going to call this A sub E, and this is just going to be an effective area. So as we continue to learn about tension member limit states, we'll see that the effective area is going to equal the net section area times another factor that we're going to talk in a little bit. Phi for fracture is given to us as 0.75. And if we think about this logically, we know that fracture is more severe, and so we want to have a larger reduction to our strength so that we're more assured that fracture won't happen in our connection.
All right, now that we've talked about yielding, we also have to consider fracture. So we said that fracture is probably going to happen where we have lower area or reduced cross-sectional area because of these bolt holes. So if I pull on this, what would you expect to happen? Hopefully you expected something like this to happen. You would see that we'd expect failure, and now relative to where the force is, we will always expect failure at kind of the forward edge of the connection. So that's this first bolt line after the main member. And we would expect it to separate something like this. Now, when we're coming up with the capacity of that, we now have to use this reduced cross-sectional area to come up with that capacity. So basically, the net section area for this particular member is going to be the area that you see in white here. And so all we're going to do is come up with a formula that describes that cross-sectional area.
This is where we get to put your engineering graphics skills to the test. So you saw in that image that we want to calculate that cross-sectional area for that reduced section, for the net section area. And so go ahead and sketch that area into your notes here. This will be good practice for you to make sure we have three-dimensional images. You can even think about our project and how you're going to create a three-dimensional model for that. Alright, so that is approximately what we saw that we need to come up with the net section area. I'm going to shade in the net section area in blue here. It's these three rectangles on the front face of the connection here. Alright, a few geometry. This plate has a thickness of T. It has a width of W. We have some diameter D. I think we're ready to make an expression. So I want to come up with an expression for that area in blue, or what we call the net section area. And so the net section area is going to equal, well, width times thickness, right? But the width has some losses. So I'm going to do width minus 2 times D. So 2 because there's 2 bolt holes, 2 diameters that are missing. And then if I multiply that by t, that would give me an expression for this net area. So all we're doing here is just geometry. I multiply that through, that gives me Wt minus 2 dt. And I want you to recognize that Wt is how we calculate the gross area for a plate member. So we're going to generalize the net section area formula in terms of the gross area. It's not too difficult for plate members, but when we start working with W sections or channel sections or angles, it's a lot easier to take the gross cross-sectional area and then subtract out the differences, since we'll be able to pull that gross cross-sectional area from the manual. Now the big question is, what do we need to use for D? So we have a few options, right? We're given in our problem, in our example, that we have 1-inch diameter bolts. However, we might not want to use the diameter of the bolt, because if we actually made our plates with the diameter of the hole equal to the diameter of the bolt, we wouldn't be able to fit the bolts inside, right? Because what if they're off by 1/1000th of an inch? When you're trying to move 1/1000th inch of steel, that's pretty difficult. So we actually drill our holes to be 1/16 inch bigger than whatever the nominal diameter of the bolt is. So perhaps, when we do this cross-sectional area, we should take into account the actual diameter of the hole. However, we'll see that not only do we have to account for the diameter of the hole, it also matters how we make that hole. And so we're going to add in what we call a 1/16 inch for damage. Okay, and this just comes out by the different fabrication processes that can be used to come up with the diameter of the hole. I'll talk a little bit more about these in a second. For now, we'll write a general formula for the net section area. That's going to be the gross sectional area minus N. N is just the number of bolts through the cross section of the member. So in this case, it was 2. So we have AG minus N times diameter of the bolt plus a 1/16 inch for the hole plus a 1/16 inch for damage. And so that gives us a final result that the net section area is equal to the gross sectional area minus N times the diameter of the bolt plus 1/8 of an inch times the thickness. Alright, so let's explore more about these extra additions.
Okay, so I just described there what we're going to use as the effective diameter of the hole. And I just want to remember, as engineers, we can't forget to be practical, right? So you guys are all engineers because you want to be practical. And so when we come up with the design kind of distance here for this bolt diameter, we can't just go with the bolt diameter. For instance, I made 1-inch holes into this particular member, but this is a 1-inch bolt. And as you can see, it doesn't really fit well. I can force it through because this is, it's styrofoam. But you can see that it's going to cause some sort of problems in there. So I can't use the same diameter hole as I use for the bolt. I have to drill a larger diameter for the hole. So that's why we have the 1/16 inch extra for the hole diameter. Now that we've learned why we have to drill the holes 1/16 inch larger than the bolt, we also have to talk about how we make these holes. So if we come in here and we're real careful and we drill a nice hole with a drill press, we're going to get something that looks like this. It's a nice smooth surface, a nice surface, not a lot of damage that occurs. But this is not very fast to do for design. So a lot of times for plate members like this, we'll punch them. And think of just like your 3-hole punch that you punch for your papers, right? It's just like you have a die and you have the punch and you just drive it through. And so that's what we're going to do. But when we do that, we get something that looks like this. This is a 1-inch punch. And you can see that there's a lot of damage that occurs on that surface. And so because of that damage, we add an extra 1/16 inch to the effective diameter of the bolt that we need to use for design. So now that's why for fracture, we use the diameter of the bolt plus a 1/16 inch the hole diameter plus a 1/16 inch of damage. So that gives us the diameter of the bolt plus 1/8 of an inch.
Returning to our example, we want to check the fracture strength. And in this example, we're going to assume that the effective area is equal to the net section area. And that is true for this connection. So back to our general equation, P sub u has to be less than or equal to phi Pn. We said that P sub u would then have to be less than our phi factor for fracture is 0.75 times F sub u times AE. For A36 steel, we know that F sub u is 58 KSI. And in this problem, we're given that the effective area equals the net area. And the net area we calculate on the previous page was the formula Ag minus N times D of the bolt plus 1/8 inch times T. So let's go ahead and calculate the net section area. Our gross sectional area from the yielding was 8 inches squared, minus we see that this connection has 2 bolt diameters that have to be taken into account. The nominal bolt diameter is 1 inch. We add the 1/8 inch to that, and then we multiply by the thickness of the plate, which is 1 inch. So that gives us a net section area that is equal to 8 minus 2 times 1.125. So that's going to give us 5.75 inches squared. All right, again, for A36 steel, F sub u is 58 KSI. We multiply that by 5.75 inches squared, make sure we have the phi factor in there, and we can get to our answer, which is going to be P sub u has to be less than or equal to 250.1 kips. Finally, we have to select the lower of these two limit states, right? So in order to have a safe design, for yielding, we have to be lower than 259.2 kips. For fracture, we have to be less than 250.1 kips. And so in this particular case, our fracture will control. And for the A36 members, we should have P sub u be less than 250.1 kips. So this is going to be our design strength. P sub u has to be less than 250.1 kips, and we say fracture controls this design. All right, so hopefully you have this kind of processed. We're going to do this again for part B. Part B has a different grade of steel, so it's now an A572 grade 50 steel. Mostly repeating these same calculations, so please go ahead and pause the video and try part B on your own. All right, presumably you're back and you finished part B already, so I'm just going to fly through this really quickly. Okay, so hopefully you got to those answers. So much like the part A, fracture controlled the design of part B for the grade 50 steel. In part C, we want to actually draw some meaningful conclusions from this. So we take a look at the capacities of both the connection for A36 steel and for the grade 50 steel. And so I'm just going to summarize them here. For the A36 steel, we said P sub u has to be less than or equal to 250.1 kips, whereas for the A572 grade 50 steel, we said P sub u has to be less than or equal to 280.3 kips. So I think the first conclusion you can draw is that when you move to a higher grade steel, right, it's P sub u goes up. And so that's generally true. A higher yield strength and higher fracture strength are going to result in higher, a better ability to hold larger loads. So that can be your first kind of conclusion. That's a very surface level conclusion, and I think we all kind of would have guessed this from the beginning. But I want to take a look a little bit deeper at this to figure out what's going on in terms of yielding and fracture, and how can we design good connections. So let's take a look at the relative increase of capacity from A36 to grade 50 steel. In the case where fracture controls, we don't see the whole benefit of moving up in the grade of steel. So I'll say, however, since fracture controls for both, the strength increase of the connection is somewhat small. And we'll quantify this. So if we do a couple calculations, we'll see that we're going from 250.1 kips to 280.3 kips. But when we look at the yield strength, or the change in the yield strength, we see that in the yield strength, we went from 259.2 for A36 steel and up to 360 kips for grade 50. So that's a huge jump in the yield strength, right? And so you're paying for a better material. So you're expecting these big increases in strength. But since fracture controlled in this case, we weren't really able to get to that big increase. So we saw only about a 12% increase in strength, even though the jump from 36 KSI to 50 KSI, or the jump from 259.2 to 360 kips, is much larger than 12%. It's actually, in fact, a 39% increase. And so that's kind of one of the things we want to think about, is when we have connections that are limited by fracture, we might not be utilizing the material to its best ability. If you're in a situation where you're kind of stuck and you have to come up with more capacity, so say 250.1 or 280.3 wasn't enough, how do we improve the strength of the connection? I just want to go back to our formulas for yield strength and for fracture strength, and just take a look at the ways we can increase their strength. So obviously we can increase by going to better materials, as we did here, Fy and F sub u. We can also increase the thickness of different elements. We could increase the width of the plates. And finally, we could look at decreasing perhaps the hole diameters, right? Because in the net section area, we had to lose those hole diameters. Now, again, this is all subject to, making sure that, a lower size bolt diameter would still work for your strength.